Hi everyone and welcome to my YouTube channel Math Puzzle with Q. Today we are going to explore an interesting problem that is called fox in a hole. So if you search on Google you can find the description of this problem, and you can find like many other people describe the most efficient strategy to solve this problem. So let's go ahead and start defining the problem. Imagine that you have 5 holes distributed this way in a line, and you have a fox that is hiding in one of these 5 holes. And every day what the fox can do is that it can jump either to the right or to the left, but it cannot stay in the same place. And every day the fox is moving this way, going either to the hole directly on the right or the hole directly on the left. So what you want to do is to catch the fox. And the only thing that you can do is that every day you come and check only one of the holes. And so the question is, what is the best strategy for you to make sure to catch the fox eventually? And we also want to know what is the minimum, the strategy that leads to the minimum number of days to catch the fox. So what I think is an innovative way to solve this problem is to represent the problem in a space-time diagram. So what we're going to do is to represent the 5 holes spread in a line this way. And so here you have the space axis with the 5 holes distributed in line, and here you would have the time axis, so the time representing the number of days. So of course the position of the holes is not going to change from one day to the next. So you are going to have the same 5 holes that are being distributed this way. And we will see that thanks to this space-time diagram of the holes and the movement of the fox that we are going to represent in this diagram, we are going to prove the efficient way to catch the fox in the minimum number of days. Let's associate a number to each of the holes right here. And let's also represent the number of days in the y-axis. Now we are going to assume that the fox starts hiding in a hole that has an even number. And we're going to represent this number in red. So if the fox starts hiding in the hole number 2 or 4, we are going to show all the paths that he can take from these holes. So the fox can only jump to the left or to the right. And same thing for number 4, the fox can only jump to the left or to the right. And so we're going to continue representing all the possible movement of the fox by representing this jump from one day to the next, to the left and to the right. And here you have the complete representation of all the movements that the fox can do. Let's do the same thing, but this time assuming that the fox will start from the hole number 3, 4, or 5, so an odd number. We're going to represent this path in green. So if the fox starts from the number 1, it can only jump to the right, so he's going to follow this path. But then from this hole, he can jump to the left or to the right. And we can therefore represent all the possible paths in green, and you are going to have this other grid that represents all the possible movement that the fox can make if it starts in the hole number 1, 3, or 5. And of course, the fox can only move forward in time, so we can represent this path by little arrow that are going always to the down direction, like this. So now let's imagine that the fox starts from the hole number 2 or number 4. So what is obvious is that the fox can only navigate on the red grid. What you can see is that the red and the green grid are completely independent. If the fox starts from a hole that is an odd number, it will only be evolved on the green grid. But if the fox starts from a hole that is an even number, it will only be able to move on the red grid. Now what you can see is that if you want to find a strategy to make sure to catch the fox, you need to identify a set of points that is going to cross all the possible paths that the fox can take. The only difficulty here is that, of course, you cannot check many holes at the same time, which means that this kind of horizontal line like that would obviously cross all the possible paths, but is not allowed because it would mean that you can only do that if you check all the holes at the same time. And remember that you can only check one hole per day. So because you can only check one hole per day, the only kind of straight path that you can take are diagonal paths. And so, for example, this path is completely allowed. And what we can immediately see with these 3 selected points is that the fox is forced to pass by one of these points if it wants to continue going forward in time and if it wants to continue jumping to the left or the right hole. So this particular strategy described here, visiting the hole number 2 in day 3, the hole number 3 in day 4, and the hole number 4 in day 5, this particular strategy is a good strategy to catch the fox for sure if the fox started from the hole number 2 or the hole number 4. And at the day number 5, we are sure that we have eventually caught the fox. Note that we can make this strategy more efficient. Instead of starting checking the hole number 2 in day 3, we can directly start checking the hole number 2 in day 1, check the hole number 3 in day 2, and the hole number 4 in day 3. And this way, you have an efficient strategy to catch the fox maximum in day 3 if it started from the hole number 2 or the hole number 4. But the problem is that if the fox started from the hole number 1, 3, or 5, it completely escaped us and we had no way to catch it. In that case, if we were not able to catch the fox after day number 3, we know that the fox started from the hole number 1, 3, or 5, and we are going to catch the fox using the same strategy, but instead of checking the holes on the red grid, we are going to check the same holes but on the green grid. And so what happens is that if we check the hole number 2 in day number 4, hole number 3 in day number 5, and hole number 4 in day number 6, if we follow this path right after, then we can see that here as well we are cutting all the possible green paths and we are going to catch the fox eventually. With this strategy, we are checking the hole number 2, 3, 4, and then again 2, 3, 4, and we guarantee that we are going to catch the fox maximum in the day number 6. One thing that you can notice is that this solution is actually perfectly symmetrical, which means that if we had checked the hole number 432 and then again 432 here, then we also would have been able to catch the fox eventually. So the symmetrical solution 432, 432 would have perfectly worked as well. What would have happened if we had checked the odd number first instead of the even number? When in that case, we would have checked all the dots represented here. And if we didn't catch the fox eventually, we would have needed to check another path. That's the path in red that would start from right here. And in that case, you see that it's a less efficient strategy because we are forced to check 5 days for the green grid and then 5 days again for the red grid. In total, we would have been able to guarantee to catch the fox only after 10 days instead of 6. So it's actually more efficient to start from the red grid because it doesn't start from one of the extreme holes, but it starts from a hole that is more in between. So thanks to this diagram, we have proven that the most efficient strategy to catch the fox was to do it in 6 days only by checking the hole number 2, 3, 4, and then 2, 3, 4 again. So I would like to dive deeper into this problem to check what is the actual probability that we catch the fox in any given day number using the strategy that we have described here. So what we have shown is that from day number 6, the probability to catch the fox is 100%. So from day number 7, it's also 100% because we caught it in day number 6, etc., etc. But what is the probability to catch the fox in day number 1, 2, 3, 4, and 5? So this is what we're going to explore here. For day number 1, the solution is very easy. You check the hole number 2, and the probability of the fox being in the hole number 2 when you check it is exactly equal to 1/5. And this is the probability to catch the fox in day 1. Now, what is the probability to catch the fox in day 2? Let's go back to the diagram above. To be able to catch the fox in day 2, the fox has to reach the hole number 3 in day 2. The only way the fox can reach this hole is to start from the hole number 2 and go to hole number 3, or the hole number 4 and go to hole number 3. What we can see is that when the fox is in hole number 2 or hole number 4, the fox can go both either to the right or to the left. So in each case, there is half a chance that it will actually go to the hole number 3 after starting from the hole number 2 or hole number 4. So the probability is equal to 1/5, that's the probability of being in the hole number 2, multiplied by 1/2, that's the probability of jumping to hole number 3, plus 1/5, the probability of being in the hole number 4, multiplied by 1/2, probability to jump to the hole number 3. So in total, the probability is equal to 1/10 plus 1/10, which is equal to 1/5. Actually, this is not completely true. If we had started from the hole number 2, we would have been caught directly in day 1 because we checked the hole number 2 in day 1. So we have to remove this probability. So the real probability of catching the fox in day number 2 is actually equal to 1/10. What about day 3? Well, let's check all the possible paths and make sure that we were not in the previous hole where we could have catch the fox in day number 1 or day number 2. So to catch the fox in day number 3, we have to be able to catch the fox here. So remember, we don't take into account the path of the fox going here or there, because in that case we would have caught the fox in day number 1 or day number 2. So the only way for the fox to reach the hole number 4 in day number 3 is to take this path represented here. And the probability to take this path is the probability of starting in hole number 4, which is 1/5, the probability of jumping to the right, which is 1/2, and then the probability of jumping to the left, which is not equal to 1/2 in that case, because that's the only way the fox can jump. The fox cannot jump in that direction, so there is a probability of 1 to jump to the left. Therefore, the probability of catching the fox in the day number 3 is equal to 1/5 multiplied by 1/2 multiplied by 1, which is equal to 1/10 again. Let's continue with day number 4. So in day number 4, we have to catch the fox where we are checking, which is right here. So for day 4, so in that case, we know that if we catch the fox in day number 4, the fox started from an odd number, so from 1, 3, or 5, and not from 2 and 4. So the path that the fox could take so we can catch it in its day number 4 is this one, but also this one. So that's all the path for if we start in 1. If we start in 3, we have this path, but also this path. And finally, if we start in 5, we have only this path. Let's go ahead and translate this into probability. So if we start from the whole number 1, we have a probability of 1/5 to start from this whole. And then we can only go to the right and 1/2 to go to the left and only 1 probability to go to the right. So we have 1 multiplied by 1/2 multiplied by 1 plus another path. 1 probability equal to 1 to go to the right, probability 1/2 to go to the right, and 1/2 to go to the left. So 1 multiplied by 1/2 multiplied by 1/2. So that's it for the whole number 1. Now what about the whole number 3? We have a probability of 1/5 to start from that whole, and then 1/2, 1/2, 1/2, or 1/2, 1/2, 1/2. So we have 2 times 1 divided by 2 to the power 3 plus 1/5. So we start from the whole number 5. Probability equal to 1 to go directly to whole number 4. 1/2 and 1/2. So in total we have 1 divided by 2 to the power of 2. This is equal to 1/5 in all cases, multiplied by 1/2 plus 1/4 plus 2 divided by 8, which is 1/4, plus 1/4. So 3/4 plus 2/4, 5/4, we have a total probability of 1 divided by 5 plus 5 divided by, multiplied by 5 divided by 4, which is equal to 1 divided by 4. Actually, this is not correct. I forgot one more path. The path that is going from here, there, and finally there. So we have a probability of 1/2 here, multiplied by 1/2, and a probability equal to 1 to go to the right in that case. So we have to add this probability here, plus 1 divided by 2 square. And in that case, we have an additional quarter. So in total, we have 6 divided by 4 here. So 3 divided by 2. And this is equal to 3 divided by 10. So that's the probability to catch the fox in day number 4. Let's continue with day number 5. So for day 5, we have to catch the fox in that specific point. So let's go ahead and enumerate the path. So let's assume we start from the whole number 1. We have this possible path. So 1, 2, 3. No, we cannot go there because then we would have been caught in the day number 4. So the possible path is this one, probability of 1. This one, probability of 1/2. This one, probability of 1/2. And this one. So in total, we have 1, 1/2, 1/2, 1/2. So 1 divided by 2 to the power of 3. And it seems like that's the only possible path if we start from the whole number 1. So what about whole number 3? In that case, we can go here, probability of 1/2, 1, 2, 3, 4. Or 1, 2, 3, 4. And 1, 2, 3, 4. So here again we are doing 4 steps, but when we arrive here, there is only a probability of 1 to jump from this specific hole. So we have to add 1 divided by 2 to the power of 3. What happens if we start from the hole number 5? In that case, we have a probability of 1 to jump to hole number 4. And then we have 1, 2, 3, and 1, 2, and 3. So the first path has a probability of 1, 1/2, 1/2, 1/2. So 1 divided by 2 to the power 3. And the other path is 1, 1/2, 1, 1/2. So probability of 1 divided by 2 to the power of 2. If we start from the whole number 1, we have a probability to be caught in day number 5 of 1/8. For this one, we have 1/8 plus 1/8, so 2/8 or 1/4. And if we start from the whole number 5, we have a probability of 1/8 plus 1/4, so 3/8. Therefore, the total probability to be caught in day number 5 is equal to 1/5 of 1/8 plus 1/4, so 2/8, plus 3/8, which is equal to 1/5 multiplied by 1 plus 2 plus 3, so 6/8, which is equal to 3/4. So we have 3 divided by 20. Finally, let's calculate the same probability of being caught in day number 6. So let's go back to all the possible paths that we have here. So to be caught in day number 6, we have to catch the fox right here. And the probability of catching the fox in day number 6, let's start from the whole number 1. So what's going to happen is that the fox, if it starts in whole number 1, it has to follow this straight path and then turn to the left. So to do that, we have 1, 1/2, 1/2, 1/2, 1/2. So 1, 2, 3, no, not 1/2 for the last one. So we have 1/2 that is multiplied 1, 2, 3 times only. So 1 divided by 2 to the power of 3. If we start from the whole number 3, in that case, we can use this path. Here, continue here, and go there. So we have 1/2 that is multiplied 1, 2, 3, 4 times. Or we can use that path, 1, 2, 3, 4. And the probability at the end is only 1. Or we can use that path, 1, 2, 3, 4. So 1/2, 1/2, 1, 1/2. So plus 1 divided by 2 to the power 3. And a priori, that's the only other path that we can take from the whole number 3. If we start from whole number 5, in that case, we can use either the path that will go all the way to the left as much as we can, and then all the way to the right, and then finally jump to the whole number 6. So we have probability of 1, 1/2, 1/2, 1/2. So probability of 1 divided by 2 to the power 3. Or we can do 1, 2, 3, 4, 5. So probability of 1, 1/2, 1, 1/2. So probability of 1 divided by 2 to the power of 2. Let's simplify this again. So here for the path, if we start in whole 1 and end up being caught in the day number 6, the probability is equal to 1/8. Here we have 1/16 2 times plus 1/8, so we have 2/8. And finally, for the last one, we have 1/8 plus 2/8, which is equal to 3/8. So total probability of 1 plus 2 plus 3, so 6/8. So for day 6, we will have as well 1 divided by 5 multiplied by 6/8, which is also equal to 3 divided by 20. So now let's add up the cumulative sum of probability and make sure that the total add up to a probability of 100% in the day number 6. So the probability of catching the fox, let's call this probability D, the day when we catch the fox. So D is lower than 1 is equal to, well, that's the probability of catching the fox in day number 1 is equal to 1/5. Probability of catching the fox in the day number 1 or 2 is equal to 1/5 plus 1/10. So this is equal to 3/10. Probability of catching the fox in before the day number 3 included, is equal to 3 divided by 10 plus 1/10. So this is equal to 4 divided by 10 or 2 divided by 5. The probability that we catch the fox before the day number 4 included, is equal to 2 divided by 5 plus 3 divided by 10. So we have 7 divided by 10. For a day before 5, we have 7 divided by 10 plus 3 divided by 20. So this gives 17 divided by 20. And finally, the probability that we catch the fox before or on the day number 6 is equal to 17 divided by 20 plus 3 divided by 20, which give a probability of 100%. So we prove also with probability that with this strategy, 2, 3, 4, 2, 3, 4, the probability of catching the fox before or on the day number 6 is equal to 100%.